Good morning, all of you. Welcome to CJ in the Rank Zone. So today we are discussing now lecture 2, that is chemical bonding and molecular structure. In lecture 1, we have discussed complete about ionic compounds. Now in this lecture, we are going to discuss about next topic in this chapter, that is covalent bond. I hope it is clear now. So in first lecture we have done, that is ionic compounds, complete about ionic compound, how a ionic bond is formed, what are different topics in ionic compounds, how they ask in the examination also we discussed. Now we are going to discuss the second concept, that is called covalent bond. So covalent bond, now we are going to start. We're going to start covalent bond now. So what is covalent bond? A covalent bond is formed between two atoms by sharing of electron pairs between them. In case of ionic bond, transfer of electrons takes place. Now a covalent bond is formed between two atoms by sharing of electrons between them. The concept of covalent bond is introduced by Langmuir, and which rules out Lewis' assumption of the cubical arrangement of octet. So the cubical arrangement of octet. So the atoms can form, two atoms combined together by the means of sharing of electron pairs. So here is a new concept comes, that is called sharing. Sharing means sharing of electrons between them. So for example, now formation of chlorine molecule. So you know the electron configuration of chlorine is neon. Neon is the atomic number 10. So 1s2 2s2 2p6. Instead of writing 1s2 2s2 2p6, we have taken neon, and that is inert gas configuration representation 3s2 3p5. So if you see here 3p5 is the having incomplete octet. Means if it is getting one electron, then it becomes stable. So it has one electron short to attain the stable configuration of argon, that is 3s2 3p6. Hence two atoms of chlorine share one pair of electrons between them, and each chlorine atom contribute one electron for sharing. This is represented as Lewis dot diagram. So total 7 electrons in the valence shell of chlorine, and these 7 electrons combined together, they share one electron. The sharing part is then done by one diagram like common. So one electron is shared by this chlorine, another electron is shared by this chlorine. The above structure is known as Lewis dot structure, and hence the formation of chlorine molecule takes place. And this type of bond formation between them is called covalent bond. So I hope it is clear. So this is called covalent bond. Very easy to understand. So the electronic configuration of chlorine is 3s2 3p5. It requires one electron to attain stability. So that one electron it will share with another chlorine, and so these two chlorine atoms together, they combine together to form chlorine molecule, that is diatomic molecule Cl2, where they get stability. I hope it is clear. Next, most of them properties of covalent compounds. Now we are going to discuss. Before this, let us see what it has given. So after this, we have properties of covalent compounds. There is no much explanation required in covalent compounds, because that is nothing but sharing of one electron. If they share one electron, they form single covalent bond. If they share two electrons, they form double covalent bond. Here I'm writing here. Just concentrate before going to properties of solids, properties of covalent compounds. So if one electron is shared between two atoms, one electron is shared, it is single covalent bond, like in case of chlorine or hydrogen, etc. Single covalent bond. Suppose if you take oxygen case, they share two electrons. Oxygen molecule, they share two electrons. Then they are represented by double covalent bond, that is O double bond O. Similarly, nitrogen will share three electrons. If they share three electrons, they form triple covalent bond, that is N triple bond N. I hope it is clear. So types of covalent bonds, we have, already know these types of covalent bonds in 10th class level. So that's why we are not discussing that. So one electron, single covalent bond. If they share one electron each, like in the case of chlorine, hydrogen, etc., they share one electron each. And two electrons, like in case of oxygen, three electrons they share with each other, they form triple covalent bond. So this is triple covalent bond, this is double covalent bond, this is single covalent bond. I hope it is clear now. So let us see what are the properties of covalent compounds. So properties of covalent compounds we are doing now. Most of them are soft solids, liquids, or gas at room temperature. Like in ionic compounds, most of the ionic compounds are solids at room temperature. But here in covalent compounds, they are gases, they can be liquids, they can be solids. So bad conductors due to absence of free electrons. All covalent compounds are bad conductors of electricity because they do not have free electrons like in the case of metals or ions. And all covalent compounds mostly soluble in non-polar solvents and sparingly soluble in water. Sparingly means very lightly. So almost all covalent bonds. So ionic compounds, they are soluble in polar solvents, but covalent compounds, they are non-polar solvents. They are soluble in non-polar solvents. What are non-polar solvents we have? Like benzene, ether, alcohol, etc. So non-polar solvents here, I'm writing underlining this. They are nothing but benzene, ether, alcohols, etc. These are nothing but alkaline compounds. So these are all called non-polar solvents. So all covalent compounds will dissolve in non-polar solvents such as benzene, ether, alcohols, etc. I hope it is clear. So they are soluble in non-polar solvents. Here and I'm underlying non-polar solvents, very important. So sparingly soluble salts in water. So they are very less soluble in water. And very important point, in ionic bond, we don't have. Ionic bond is not directional, whereas covalent bond is directional bond because covalent bond is directional bond and compounds exhibit isomerism. Isomerism means compounds having similar molecular formula but different structural formula. So what is isomerism? You'll get this in organic chemistry and even in inorganic chemistry also. So what is isomerism? I'm writing here. Organic compounds having, so compounds having same molecular formula but different different structure formula. Structural formula. They are called as isomers, and the phenomenon is called as isomerism. Usually, these type of isomerisms exhibit in organic compounds, even covalent bond compounds also. So I'm clearing it now. So directional bond and exhibit isomerism. These 2 points are very key. And soft solids, liquids are gas at room temperature. So they have low melting points and low boiling points. By this, we can say soft solids, liquids, or gases means they have very low melting points as well as boiling points. Not like case of ionic compounds. Ionic compounds have high melting points and boiling points. So I hope it is clear. These are the important properties of covalent compounds. More about covalent compounds. Let us see now. So each bond, features of Lewis structures. Each bond is formed as a result of sharing an electron pair between two atoms. Each bond atom contributes at least one electron for sharing. So sharing means definitely the contribution is from both sides. Very important, both sides, because one element cannot share itself. So both the atoms which are combined together, they share with each other. Either they share one electron each, or two electron each, or three electron each. So the bonded atoms attain stable octet configuration after sharing the electron pairs. That is very important. Why do they share only one electron? Because they require only one electron. If they require two electrons, they share two electrons. And if they require three electrons, they share three electrons. So the bonded atoms attain stable octet configuration after sharing the electron pairs only. If only one electron is shared, the atoms are said to be bonded by single covalent bond. As I already explained you, so single covalent bond will be like this, just a small dash. This is called single covalent bond. So if only one electron is shared between, if only one electron pair is shared between each, means one atom will share one electron, another atom will share another electron. So in that case, it is called as single covalent bond. Suppose if two electron pairs are shared between two atoms, then they are said to be bonded by double covalent bond. So for example, as I told you, oxygen O double bond O, because they share two electrons each. Means if you write the structure here, they share two electrons from this oxygen and two electrons from this oxygen. So as they are sharing two electrons each, so we'll say it is called double covalent bond. If three electron pairs like nitrogen triple covalent bond. So as they are sharing three electrons between each other, so 1, 2, 3 for one this nitrogen, and 1, 2, 3 for this nitrogen. So as they are sharing total 6 electrons. and they are sharing total 6 electrons, we'll say triple covalent bond. 4 electrons, double covalent bond. 2 electrons, single covalent bond. So no 1 electron sharing. So I hope it is clear. Next, we'll continue with this covalent compounds. So if 2 electron pairs are shared between two atoms, they are said to be bonded by double covalent bond. Between two atoms, if 3 electron pairs are shared, pairs means two electrons. So 3 pairs means 6. I hope it is clear. Next. So example water. In water, in the case of water, oxygen has how many valence electrons? It has 6 valence electrons. It has how many valence electrons? 6 valence electrons. 4 will be unshared and 2 will be shared. Here, so you can see here the diagram. You can clearly, it is visible. So total 1, 2, 3, 4 electrons, and here one single 2 electrons are shared by 2 hydrogen atoms because oxygen has atomic number 8. So it has configuration 1s2, 2s2, 2p, 4. So still it requires 2 more electrons for attaining stability. So the 2 electrons will be shared by 2 hydrogen atoms. So on the whole, and hydrogen, in turn hydrogen, if you take hydrogen atomic number is 1, so its configuration is 1s1. So this hydrogen requires 1 electron, this hydrogen also requires 1 electron. So on the whole, they share with each other, they share with oxygen and forms finally water molecule. Next, you take in consideration carbon tetrachloride. Carbon tetrachloride, each carbon has 4 electrons in the valence shell, and each chlorine requires 1 electron. So this carbon requires more 4 electrons because carbon atomic number is 6. So configuration is 1s2, 2s2, 2p2. So it requires 4 more electrons for attaining stability that are found, from which it will get sharing from 4 chlorine atoms. So then it forms a this is called sharing part. You can see here 2, 2, 2, and 2. So in total it is carbon tetrachloride. It is nothing but sharing of electrons. I hope it is clear. So if they share only 2 electrons, here why we are getting single bond? Because this carbon is sharing 1 electron, this chlorine is sharing 1 electron. So between these two, single covalent bond. Between these two, single covalent. Between these two. Like this, here water also we have only single covalent bond. We do not have double covalent bond here. So I hope it is clear. Next, some more examples. Carbon dioxide. Let us see into the consideration of carbon dioxide. Here you see this carbon is sharing 2 electrons. It becomes double bond, means this oxygen is sharing 2 electrons and this carbon is also sharing. Because oxygen requires 2 electrons, carbon requires 4 electrons. So from this side it is getting 2 electrons, from this side it is getting 2 electrons. So on the whole, carbon becomes stable. So I'm writing here simply in simple words. So from this side it is getting 2 electrons, it is sharing 2 electrons, and from this side it is sharing 2 electrons. So on the whole, it becomes 4. So this is nothing but C double bond O double bond O. Well, so by these fluid structures, we can even guess the structures of covalent compounds. So this is called carbon dioxide molecule. Next, ethene molecule. Its formula is C2H4. So two carbons shares 4 hydrogens. So this carbon requires 4 electrons. So 1, 2. So here 1 electron, because single bond means 1 electron. Single bond means 1 electron. And here it is sharing in between one more carbon, 2 electrons. So on the whole, it becomes 4. So in this way, they attain stability. I hope it is clear. So if they are sharing 2 electron pairs, it is nothing but double bond. If they are sharing 1 electron pair, single covalent bond. If they are sharing 2 electron pairs, here also 2 electron pairs, double bond. See, 1 electron pair, single bond. 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 On the whole, you will get 4 single covalent bonds in ethene and 1 double bond you will get. So total 5. I hope it is clear. Next. Nitrogen molecule, as I told you, nitrogen has 5 electrons in the valence shell. It requires 3 more electrons, so it will share its 3 electrons to this nitrogen, and this nitrogen also in turn shares 3 electrons. On the whole, they will share 6 electrons, as they are sharing 6 electrons and 3 electrons each. So they are getting triple covalent bond. The same acetylene also example. Acetylene, this between two carbons, 3 electrons are shared, and this 1 electron is shared with 1 hydrogen, 1 electron is shared with. So on the whole, this carbon is getting 4, this carbon is also getting 4, because here we are getting commonly it is getting 3 electrons. So as it is getting commonly 3 electrons, so here it is 3 electrons. I'm writing here 3 electrons. So here also 3 electrons. So as it is sharing 3 electrons, it is totally this side 1 electron. So 1 electron, 3 electrons. I'm writing it properly. You can just see. So it is 3 electrons. So 3 electron, 1 electron. So this is 3 electron. This is also 1 electron. So on the whole, it is shares 4 electrons because carbon requires 4 electrons for its stability. So I hope it is clear. So whenever it shares 1 electron, it is single covalent bond, 2 electrons, double covalent bond, 3 electrons, triple covalent bond. So with these examples, it is clear. So these are Lewis structures of some of the covalent compounds. All these are covalent compounds because mainly covalent compounds are found between metal and non-metal. No, it is metal, non-metal and non-metal combination. So all covalent compounds is nothing but non-metal combination. Non-metal plus non-metal combination. So non-metal combination is nothing but covalent bond. So this you have to make it clear because ionic bond is metal and non-metal combination, but covalent bond is non-metal combination. I hope it is clear. Next, steps to follow to represent steps to be followed to represent a molecule in Lewis structure. So what are the steps to be followed? In order to write the Lewis structure, first the total number of valence electrons of all the atoms of the molecule should be calculated. First we should know. This is not even required to calculate. You have to remember, if you remember the group number, automatically you'll get number of valence electrons. If you remember group number, so I'm writing here. So if you remember group number, so number of valence electrons will be based on group. For example, first group, it has only one valence electron. 15th group, so if you know group number of the elements, combining elements, easily you can identify number of valence electrons. So to find, in order to write the Lewis structure, the total number of valence electrons, first the total number of valence electrons of all the atoms of the molecule should be calculated. For example, in methane, there are 4 valence electrons in carbon and 1 valence electron each in hydrogen atoms. So I'm writing it clear. So 1 valence electron each in hydrogen atom. So the total number of electrons is 8. So in this way, you'll write here. So it's called covalent bonding. Next, for cation removal. For cation removal of 1 electron for each positive charge and for anion 1 electron to be added to the valence electrons for each negative charge. What is this? Cation removal of 1 electron for each positive charge and for anion 1 electron to be added to the valence electron for each negative charge. For example, hydroxide ion OH minus, the total number of valence electrons of oxygen and hydrogen is 7 and one more electron is added here. So due to the negative charge on 1 electron, and hence the total number of valence electrons should be 8. This is very important. Oxygen is, how many valence electrons for oxygen? 6. And hydrogen is 1. So 1 and minus 1 is there. So it is becoming 8. I hope it is clear. Next. So knowing the skeletal structure of the molecule, the total number of electrons are distributed as bonded or shared electron pairs between these atoms. Generally, less electronegative atom will be the central atom. Very important here. Less electronegative atom. For example, in case of carbon, methane, carbon is a central atom. Less electronegative atom will be the central atom, and the higher electronegative atoms will we take the terminal positions. Terminal position means outside positions. So, for example, in the case of CCl4, carbon is central atom, and chlorine is terminal positions because chlorine is more electronegative than carbon, and carbon is less electronegative than chlorine. So, chlorine take terminal positions and carbon take central position. So in this way you have to write while drawing the structure of Lewis dot structures. These are the truths. Generally less electronegative atom of the center, less electronegative atom will be the central atom and the higher electronegative atom will be the terminal, will take the terminal positions. I hope it is clear. Next. For example, in carbonate ion, carbon is central atom and oxygen is a terminal atom. Because oxygen is more electronegative than carbon, so oxygen becomes terminal. After assigning the shared electron pairs, remaining electron pairs are used to make multiple bonds or retain as the unshared electron pair of lone pair of electrons. What is this lone pair? The electrons which are not involved, the electrons which are not involved in bonding, they are called as lone pair of electrons. Like in the case of water, we have seen. So lone pair and bond pair, it's very important, which you have been discussing more in Vesper theory. So what is lone pair of electrons? The electrons which are not involved in bonding, they are called as lone pair, which are not involved in sharing. So unshared electron pair. Unshared electron pair are lone pair of electrons and atoms, taking into consideration of octet state of each of the atom. So this point is most important. After assigning the shared electron pairs, remaining electron pairs are used to make multiple bonds are written as the unshared. They are written as unshared electron pair. So this is most important. These unshared electron pairs are also called as lone pair electrons. Lone pair of electrons. Next, example one. Write the Lewis structure of ammonia. Lewis structure of ammonia. So let us take in consideration. I'm trying to draw the structure of ammonia. So first we'll write, because nitrogen is less electropositive, less electronegative than hydrogen. So hydrogen and nitrogen. So nitrogen becomes central atom. So nitrogen has how many valence electrons? 5 valence electrons. So that 5 valence electrons by writing in this way. So 1, 2, 3, 4, and 5. So these 5 valence electrons, and nitrogen requires more 3 electrons for attaining stability, because it has 5 valence electrons. It requires 3 electrons for attaining stability. So that 3 electrons will be shared by hydrogen. So this hydrogen will share 1 electron. This hydrogen will share 1 electron, and here also one hydrogen shares 1 electron. So on the whole, it has 1, 2, and 3. Total, they are sharing 3 electrons each. So 3 electrons from nitrogen, each hydrogen one electron. So it is having 3 bond pairs. What we call it as bond pairs, because they are forming 3 bonds with nitrogen, hydrogen, hydrogen, and hydrogen, and one lone pair of electrons, that is one unshared. So it has one lone pair. So this is the structure of Lewis structure of ammonia. So let us check. So it has one unpaired electrons, one lone pair, and 3 bond pairs. 3 bond pairs, because 3 hydrogens are giving three electrons. Because this hydrogen also requires 1 electron for stability. The one which is sharing, I'm giving cross mark for hydrogen. To know the difference between nitrogen and hydrogen, we are giving cross marks. Even if we don't give, also nothing will happen. So for all, you can keep dots. I hope it is clear. Now let us see the answer for structure of ammonia. You can see here nitrogen has, this is 2, and this is 2, this is 2. So it has one lone pair. So how many bond pairs? It has 3 bond pairs. This is 1, this is 2, and this is 3. So it has 3 bond pairs and one lone pair. One lone pair, LP. I hope it is clear now. So in this way, we'll draw the diagrams of Lewis structures. So nitrogen, as it's sharing 2 electrons, so we are getting nitrogen here one side, hydrogen one side, another side also single covalent bond, another side also single covalent bond, and here we'll get 2 electrons. This is actual structure of ammonia. I hope it is clear. So in this way, we'll write. For remaining also, you can write like this. Let us see next question. Question number 2. Write the Lewis structure of carbon dioxide. As we already discussed in the example, what is the Lewis structure of carbon dioxide? Carbon is a central atom because it is less electronegative than oxygen. So carbon is central atom and oxygen is more electronegative. So it becomes terminal position. It will take terminal positions. So let us see now answer. You can see here this carbon is having how many electrons? 4 electrons. As I told you, sharing one will become cross. From oxygen, it will be the electron which is shared from oxygen is represented as cross, 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 and cross. I hope it is clear. So as it is sharing 2 electrons from carbon, 2 electrons from oxygen, 2 electrons from carbon, 2 electrons from oxygen. So on the whole, the structure becomes like this. It is C double bond O, and here also double bond O. On the whole, it is getting 4 electrons. Carbon is getting 4 electrons. Oxygen is getting 2 electrons from this carbon, and this oxygen is getting 2 electrons for attaining stability. Because oxygen number of valence electrons is 6 electrons. So here also 6 electrons. So it requires only 2 electrons for its stability. So it is getting from one carbon only. I hope it is clear. Next. So example 2 is also clear. Next question. Lewis dot structure of SO4 2 minus. These type of structures are important because they'll ask ionic structures also. This is ion structure 2 minus. Which of the following represent correct structure of SO4 2 minus? This they'll ask in the examination. So let us see now. SO4 2 minus. What is this called? SO4 2 minus. So SO4 2 minus. Here this is called sulfur. Sulfur has how many valence electrons? 1, 2, 3, 4, 5, 6 electrons. So it is sharing 2 electrons with oxygen, 2 electrons with oxygen, 2 electrons with another oxygen, and the 2 electrons which is gained, that is 2 minus is there, no? So the 2 electrons which is gained, the 2 electrons which it is gained, that will be taking as this position. So on the whole SO4, because it do not have 8 electrons in the valence shell, but we'll write 8 electrons in the valence shell because 2, 2, 2 and 2, and these 8 electrons here 2 minus, so it means that 2 electrons has come into this position. So the structure of SO4 2 minus. I hope it is clear. And all the way it is sharing how many electrons in for each and every oxygen, it is sharing 2 electrons, 2 electrons, 2 electrons, 2 electrons, and in turn oxygen is sharing 2 electrons here, 2 electrons here, 2 electrons. So where you will get double bonds, very very important. I'm writing here that exact structure. So you can see here sulfur, for this oxygen it will get single bond only because it is sharing only 2 electrons. Oxygen is not sharing any electron, and for this it is sharing 2 electrons. So SO4. So for this oxygen 2 electrons, and for this oxygen 2 electrons, and this oxygen also in turn sharing 2 electrons. So we have 3 double bonds and 1 single bond, and bracket will keep, and here we'll write 2 minus. So this is the structure of SO4 2 minus. SO4, whenever they are sharing 2 electrons, so here you'll get double bond, here you'll get double bond, and here also you'll get double bond, and there you'll get single bond. So I hope it is clear. So the structure of SO4 2 minus. Next question. Example 4, write the Lewis dot structure of CO3 2 minus. Very, very important. So whenever these ionic structures are there, it's more important for examination point of view. They'll ask this type of questions. One carbon is contributing with 3 oxygen atoms and gaining in turn gaining 2 electrons. So itself we can say here this carbon requires 4 electrons for attaining stability. Two it will gain, two it will gain from 2 oxygens, and one more oxygen it has to contribute. So it is nothing but it is gaining 2 minus. As it is gaining 2 electrons extra, it is getting 2 minus. So that's why you'll get the structure CO3 2 minus. I hope it is clear. Now we'll see the structure. So as I told you, here it is gaining 2 electrons, here it is gaining 2 electrons. So 2 electrons, 2 electrons, 2 electrons, and here on the whole 2 minus. So this is the structure of CO3 2 minus. CO3 2 minus Lewis dot structure. This carbon is having 2 and 2, 4 electrons, but these 2 electrons which you have got it from here. So these 2 electrons, and this oxygen is getting 8 electrons, this oxygen is getting 8 electrons, this oxygen is also getting 8 electrons. So on the whole, it is nothing but CO3 2 minus, that is the Lewis dot structure of carbonate ion. It is called what? Carbonate ion. The name of this compound is, the species, not a compound actually. It is called as carbonate ion. I hope it is clear. Next question. Like the Lewis structure of NH4 plus. Here nitrogen requires 5 electrons. Actually, nitrogen has 5 electrons. So it is sharing with 5 hydrogens, but instead of sharing with 5 hydrogens, it is sharing with 4 hydrogens only, as you see here clearly. And as it is getting positive charge, it should lose that extra fifth electron for attaining stability. So on the whole, this is also a stable structure, and you can see the structure here. Nitrogen sharing 1 electron, one, total 4. So it will get all 4 sides single bonds, and on the whole, it will be getting less because one more electron is losing. It is losing one more electron. That is, it has 5 valence electrons, but out of which 5 it is taking only 4 valence electrons because only 4 hydrogens. See, for example, here I will write this nitrogen 5 valence electrons. So first valence electron will go to this hydrogen, second one, third one, and fourth one. And fifth one, that missing electron will come as positive charge. So on the whole, we'll keep like this. So this is called NH4 plus structure. So it is very, very simple and it's clear. And all of them will get stability because nitrogen is getting stability by accepting 4 electrons from 4 hydrogens, and 1 electron is losing. That 1 electron extra it is losing because, so it is getting on the whole 8 electrons. Next. Where the Lewis structure of PCl5, phosphorus. Actually, phosphorus has 5 valence electrons in the valence shell, and it contributes all the 5 valence electrons to 5 chlorines, so that chlorine also get 8 electrons in the valence shell, and phosphorus also getting 8 electrons in the valence shell. So you can see here, this is phosphorus pentachloride, and here you can see here, this phosphorus is giving 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, and all chlorines are getting 8 electrons in the valence shell because 2, 2, 6, and here one from chlorine, one from phosphorus. Single covalent bond means 2 electrons. Single covalent bond means 2 electrons, 2 electrons, 2 electrons, 2 electrons. So on the whole, all becomes stable. So this is the structure of PCl5. All these structures are very important in the examination. From the structures, they can ask a number of sigma bonds and pi bonds. So that concept we'll discuss in the next session. So SF6, sulfur hexafluoride. What is this called? Sulfur hexafluoride. 6 fluorines are there. We'll call it as sulfur hexafluoride. So sulfur hexafluoride. So this is called sulfur hexafluoride. So SF6. So sulfur has 6 electrons in the valence shell. All 6 electrons will be contributed to 6 fluorines, so that fluorine requires 1 electron for attaining stability. So all the fluorines will get stability as well as sulfur also. So let us see the structure of sulfur hexafluoride. In this way it will come. So 6 single covalent bonds, because it is sharing 1 electron each fluorine it is sharing only one electron. So all single covalent bonds, we are getting 6 single covalent bonds, and there is no lone pairs. All are bond pairs. Bond pairs means all the electrons are completely bonded. There is no lone pair for sulfur. For fluorines they have. And why we are taking sulfur as central atom? Because sulfur is less electronegative than fluorine. So that point is very, very important, as we are already discussing each and every structure. Next, we have example 8, structure of BCl3. What is this specialty about BCl3 and PCl5? We will discuss. That concept is called electron deficient compounds and more electron compounds. So that we'll discuss later in the concerned chapter. So BCl3, each boron will share one electron to each chlorine, and on the whole they become 6 electrons after sharing. That's why it is called as electron deficient compound, as it is sharing only 6 electrons after sharing. It is getting only 6 electrons, incomplete octet. So it is called as electron deficient compound, whereas PCl5 is electron rich compound. Electron deficient compound. What is electron deficient compound? After sharing, boron is getting only 6 electrons. This boron is getting only 6 electrons because 3 electrons it is having outermost configuration, 3 electrons it is sharing. So incomplete octet after sharing. Actually, after sharing, they should get octet configuration. But after sharing, it is getting only 6 electrons. So it is called electron deficient compound. If you take in the case of PCl5, after sharing, this phosphorus is getting 10 electrons because phosphorus has 5 electrons, and 5 electrons from each chlorine it will share. So it is getting PCl5, as you have seen the structure in the previous question. So these compounds are called as electron rich compounds. Electron rich. And these are electron deficient. Electron rich and electron deficient. I hope it is clear. So BCl3 is electron deficient, and which are electron sufficient, which have 8 electrons. If you have 8 electrons after sharing, they are called as electron sufficient compounds. Electron sufficient compounds. I hope it is clear now. So electron sufficient compounds, electron deficient compounds, and electron rich compounds. What are electron rich compounds? After sharing, if they are getting after sharing, if a particular element, a particular atom is getting more than 8 electrons, they are called as electron rich. After sharing, if they are getting less than 8 electrons, like in the case of boron, it is getting only 6 electrons, they are called electron deficient compounds. And after sharing, if they are getting 8 electrons, like in almost all the cases, they are called as electron sufficient compounds. So electron rich, electron deficient, and electron sufficient compound. This topic anyway we'll discuss in the coming sessions. So just it was an introduction. So that's why I have given. Next example, CO. Very, very easy. CO. CO means, here you can see here carbon is getting 4 electrons. It requires 4 electrons, but it is getting 3 electrons from oxygen and 2 lone pairs. So that's why we got, this is also electron deficient, because after sharing it is getting how many? 1, 2, 3, 4, 5, and here 1, 2, 3, 4, 5. So this is also electron deficient compound, CO. So I hope it is CO structure. We got as they are sharing 3 electrons each. After sharing, is getting 6 plus 2. We cannot say it is electron. It is electron sufficient only because this carbon is getting 3 electrons from oxygen. 3 electrons it has, and this it is having 2 electrons here. So same here. So this is the structure of CO as they are sharing three electrons each, three electrons. So after sharing, this has getting 8 electrons because 6 plus 2 8. After sharing, this also getting 8 electrons. I'll show it here. This is getting only 5 electrons, not 8 electrons. So this is called CO, the structure of CO. I hope it is clear. Next, example 10. All these examples are important, and most important is ozone molecule. If you know ozone structure, it's very important because they'll ask sorry, they'll ask the oxygen states of ozone molecule. So definitely it is going to come for many competitive exams already. For all many years for competitive exam it has come. So this structure is most important. You can just see the structure. So here you can see this oxygen, one single bond. It is giving one single bond means it is getting only 1 electron. So 1 electron is shared between these 2 electrons. Means one atom, 1 electron from this, 1 electron from this. And here, 2 electrons from this, 2 electrons from this. And on the whole, it has one lone pair. So this is either this representation or this representation. Double bond can come either this way or this way. So this is called ozone molecule. Very important ozone structure. Very important. So I'm just going back. So ozone structure is most important. Very important structure. You can just note down in your classworks. So ozone is very important. I hope it is clear. So in this way, we'll represent all the Lewis star structures. I hope it is clear. Next, next example, NO3 minus, nitrate ion. Nitrate ion, NO3 minus, nitrogen is given having 5 electrons and is sharing 3 electrons with oxygen, and one more electron it is getting more. So it is sharing total 3 electrons with 3 oxygens. So how the structure it could be, you can just see here. So nitrate ions, just like ozone molecule, one side is having double bond, another side is having single bond, and one electron will be getting for oxygen extra. So total oxygen is getting 6 electrons and 6 electrons. 1 electron is getting from nitrogen. So on the whole, this is stable structure of nitrate ion. So this is called nitrate ion. All this, so important structures, nitrate ion, carbonate ion, all the ionic structures are important in case of covalent compounds. And these are metal and non-metal. Nitrogen is less electronegative than oxygen, so it is taken as central atom. So I hope it is clear. Next, example 12. So formal charge on chlorine atom in HClO4. What is formal charge? We are going to discuss next. So what is formal charge of chlorine? Here they are asking formal charge of chlorine in HClO4. Let us see now. So here formal charge of chlorine is equal to total valence electrons minus 1 by 2 into bond pairs minus lone pairs. So in HClO4, how many chlorine atom is having? How many valence electrons? So I'm writing the formal charge formula here. You can just see here to find formal charge. Formal charge is equal to number of valence electrons of central atom, number of valence electrons of central atom, that is chlorine here, minus half into number of bond pairs, number of electrons shared, or you can say bond pairs, minus number of unshared electrons. So number of valence electrons of central atom minus half into number of electrons shared minus number of unshared electrons. Sorry. So in this way you can find. So chlorine has how many electrons? Total valence electrons already we know chlorine has 7. And how many electrons it shared? 1 electron with this oxygen, 1 electron, 1 electron, 1 electron. Total 4, and one from oxygen, one from oxygen, one from oxygen, one from oxygen. So 4 plus 4, 8, because it is getting 4 single bonds. I can show here the structure. So Cl here, one oxygen, one oxygen, one oxygen, and one oxygen, and HClO4. So total 4 electrons. So all the 8 electrons have been shared. 8 electrons total it is. So there is no unshared electrons. So it is 0. The formal charge of chlorine is 3. I hope it is clear. So this type of questions are most important for objective. So how to calculate formal charge? Formal charge is equal to number of valence electrons of central atom minus half into number of electrons shared minus half into half minus number of unshared electrons. Again, repeating the formula: number of valence electrons on the central atom minus half into number of electrons shared minus number of unshared electrons. This is the formula for finding formal charge. Very, very important. They will ask in the exams what is formal charge. So again, this formal charge will be discussed later. Meanwhile, this is the example. As it comes here, we have to discuss. So I have discussed. Next question: calculate the formal charge of phosphorus in H3PO4. Same formula by applying. That is, what is the formula again? I'm writing here. Formal charge. Formal charge is equal to number of valence electron of central atom. Number of valence electrons of central atom minus 1 by 2 into number of shared electrons or bond pairs, number of shared electrons minus number of unshared electrons. Unshared electrons. So this is most important. Let us see now structure. So number of electrons, phosphorus has 5 electrons minus 1 by 2 into how many electrons it shared with each oxygen, 1 electron, and oxygen in turn shared with hydrogens, and hydrogens that we cannot consider. So only 8 electrons it shared because it is with each oxygen it shares 2 electrons. See here, this is one oxygen. So I'm showing it here clear in the diagram. You can see here, this phosphorus is sharing 2 electrons with this oxygen. This is 2, this is 2, this is 2. Total it has 8 electrons. So 8 electrons it is sharing, and minus unpaired electrons on phosphorus, only on phosphorus. We should not see unpaired electrons, that is unshared electrons on oxygen and all, hydrogen also, only central atom only. Unshared electrons, number of unshared electrons on central atom. So it is 0. So on the whole, the formal charge of phosphorus in H3PO4 it is 1. I hope it is clear. Very, very important formal charge. So what is formal charge? We have discussed. More about formal charge we'll discuss when it comes. So next we are going to share. So these are the solved examples in terms of covalent compounds. Next. So new share I'm doing. Point 4. Yes, next one, next thing we're doing now. That is 12.4. Yes. So in this we are discussing now more about covalent compounds. So in the previous one we have discussed what is covalent compound and what are the examples of covalent compounds. What are the examples of covalent compounds? Now I'll discuss more about covalent compounds. So just see. So what are the limitations of octet rule? Next topic is limitations of octet rule. Octet rule is not followed by all atoms found in many molecules. This rule is applicable. Very important, you can see here. This rule is applicable only for atoms of second period in the periodic table. Yes. Very important, you can see here. This rule is applicable only for atoms of again writing clear, just wait. So this rule is applicable only for atoms of second period in the periodic table. Atoms of second period. What are the atoms of second period? We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Second period. Second period has how many electrons? How many atoms? How many elements? We have 8 elements. Second period has 8 elements. So all those 8 elements. So this octet rule is applicable only for second period in the period table. There are 3 types of exceptions of the octet rule. Incomplete octet of the central atom, as I discussed. Incomplete octet odd electron molecules, expanded octet for the central atom, like electron deficient, electron sufficient, and electron rich. So that we are going to discuss now. So what are these three? So what are the three? We have incomplete octet, incomplete octet of the second central atom, odd electron molecules, expanded octet. So these are the three rules, three types of exceptions to the octet rule. So what is octet rule? According to octet rule, an atom, so an atom, if it gains all the 8 electrons in the, after sharing or after transferring electrons, if it is getting 8 electrons, it is stable. So octet rule is not followed by all atoms found in many molecules. This rule is applicable for the atoms of second period in the periodic table only. There are three types of exceptions to the octet rule. First is incomplete octet of the central atom, odd electron molecules, expanded octet. Now we are going to discuss clearly all those things. So what are those? In some molecules, the central atom will not have octet configuration, yet the molecule exists in nature. This type of configuration of central atom is found in elements having less than 4 electrons, like lithium, beryllium, boron. So in all these elements, lithium has 1 electron in its valence shell, beryllium has 2, and boron has 3 electrons in the valence shell. So they have less than 4 valence electrons, but still after sharing, as I told you, they are electron deficient compounds. They are nothing but having incomplete octet. After sharing, they are getting only, for example, if you take into lithium hydride consideration. So lithium hydride, if you take into consideration, I'm showing it here for lithium hydride. So lithium hydride, if you take into consideration, lithium has 1 electron in the valence shell. After sharing with 1 hydrogen, it will get only 2 electrons. With 1 hydrogen it shares, it is getting only 2 electrons in the valence shell. So it is incomplete octet, but yet it is stable. So this is an exception for lithium hydride. Next we have beryllium hydride. Beryllium hydride also you can see beryllium has 1 hydrogen and 1 hydrogen this side. So we can see here, so it is sharing, after sharing it is getting only 4 electrons, because it is getting only how many electrons? 4 electrons after sharing. Still it is having less than 8 electrons. So this is also an exception. So this is nothing but all these are called electron deficient compounds or incomplete octet compounds. So these are called incomplete, less than 4 electrons. They are nothing but incomplete octet. Will not have complete octet configuration. So these are called electron deficient compounds. We can call it as electron deficient compounds, or we can say incomplete octet. After sharing, they are getting incomplete octet. So these things are very important. So make a note. Next, so example lithium hydride, barium hydride, and BCl3. As I told you, they are having only single covalent bond. So this boron is sharing with three chlorines, one electron each, and after sharing, it is getting only 6 electrons. How many getting? It is getting 6 electrons. They're showing it here. 6 electrons. So on the whole, they are sharing only 6 electrons. And here it is sharing only, it is getting only 4 electrons. And here it is getting only 2 electrons. So all these are nothing but incomplete octets. So these are nothing but what? Incomplete octet. That is first exception of octet rule. So some of them are having incomplete octets, yet they are stable. First exception, it is clear. I hope it is clear. Second exception. So odd electron molecules. In molecules having odd number of electrons, odd number means 1, 3, 5, and so on. The octet is not satisfied for all the atoms in the molecule. Example, nitric oxide, nitrogen dioxide are odd electron molecules. So what is nitric oxide? You can just see here nitric oxide. It has 3 electrons here and 2 electrons it is sharing. So this nitrogen is getting only 5 electrons. How many electrons it is getting? 5 electrons. So this is odd electron. This nitrogen, this side it is 3. Sorry, 4 plus 1, 5. And here it is 1 plus 1. So 1 plus 2, 3. So this is 2 here. And here it is 5. So because 4 plus 1, 5, 2 plus 1, 3. So on the whole, it is odd electron molecule. So odd electron molecules. So these are also after sharing, they are not getting 8 electrons in the valence shell. That is most important one. After sharing, as they are getting only odd electron molecule. So these are also an exception for octet rule, even though they are stable. They are observed as stable. That is nitric oxide as well as nitrogen dioxide. Next, expanded octet state. As I told you, electron rich compound. These are also called as what? They are also called as They are also called as electron-rich compounds. Electron-rich compounds. Why they are called as electron-rich compounds? Because after sharing, they are getting more than 8 electrons, not less than 8 or even odd number. They are getting more than 8 electrons. If you see sulfur hexafluoride, sulfur is getting how many electrons after sharing? It has 6 electrons in the valence shell, 1, 2, 3, 4, 5, 6. And each with each flow, it is sharing for one electron. So it is getting on the whole 12 electrons. How many electrons? It is getting 12 electrons. Like in the case of PC alpha, it is getting 10 electrons. PC alpha is getting after sharing phosphorus is getting 10 electrons. And H2SO4 sulfur, this is also getting more than 8 electrons. So in this way, these are nothing but what? Electron rich compound. This is also one exception to in octet rules. So incomplete octet, expanded octet, odd electron octets. So odd electron molecules. Even though they are stable, they are not following octet rules. That is, they are after sharing, they are not getting 8 electrons. They are getting less than 8 or more than 8. So exceeds 8. Such molecules are said to be in expanded octet or superoctet state. So the elements of beyond third pair make use of 3s, 3p, and 3. Why it is possible? Because it is forming because of they are having empty 3d orbital for bond formation. So 3s, 3p, and 3d electrons for bond formation. Thus, the total number of valence electrons exceeds 8. Such molecules are said to be in expanded octet or superoctet state. I hope it is clear. Next. So examples is clearly shown. So as I told you, this phosphorus is getting 1, 2, 3, 4, 5 bonds. 5 bonds means each bond 2 electrons. So it is 10. This sulfur is getting 1, 2, 3, 4, 5, 6 bonds. 6 bonds means 12 electrons. This sulfur is getting 1, 2 here, 2 means here 4, 1 plus 4, sorry, 2 plus 4, 6, 6 plus 4, 6 plus 4, 10, 10 plus 12, 12 electrons. So in this way you are getting, so this is called elements beyond third period. So this is called expanded octet state. So we have three important exceptions for octet rule. One is odd electron molecules which are stable, and the second is expanded octet, and the first one is nothing but less than number of 8 electrons. So I hope it is clear. So, and first one they are called as electron deficient molecules, second one they are called as electron deficient molecules, second one also, and third one they are called as expanded octet molecules are called as electron rich compounds. These are called what? Electron rich compounds. I hope it is clear. Next, other drawbacks of octet rule. The octet rule is based on the stability of noble gas configuration, but some of the noble gases like xenon and krypton, very important. Xenon also can form some compounds, even though it is stable, but it is forming xenon tetrachloride like XCF4, xenon dioxide, etc., and xenon dioxide, etc. So as it is forming compounds, it can form compounds with oxygen and fluorine. The octet theory does not explain the shapes of covalent molecules. So this theory does not explain the relative stabilities of molecules. So based on the stability of molecules, we can say only if the electron has 8 electrons in the valence shell, we'll say it is stable. But still, so many molecules are having less than 8 electrons, more than 8 electrons, odd electrons, but still they are stable. That stability is not explained by octet rule. I hope it is clear. So this is a drawback of octet rules. Next, formal charge. As I discussed in the previous in this section only, examples. The net charge of the ion is represented as charge on the ion as a whole, but not on the individual atoms. But it is possible to assign a formal charge on each atom of the Lewis structure. The formal charge of an atom in a molecule is defined as the difference in the number of valence electrons of atom in isolated or free state and the number of electrons assigned to the atom in the Lewis structure. Very, very important. Difference in the number of valence electrons of an atom in the isolated state. So simple formula also I have shown you in the previous examples. So how to calculate number of valence electrons in the central atom minus total number of non-bonding electrons minus 1 by 2 total number of bonded electrons. Same thing we have done. Half into total number of bonded electrons, total number of non-bonding electrons minus number of valence electrons. So this only I have written already. So I explained you in this session only. So this is the example for formal charge. So interpret the non-linear shape of H2S molecule and non-planar shape of PCl using Vesper theory. This we'll discuss after finishing Vesper theory. Some more this question has come. So the electron star structure of N2O nitrous oxide molecule can be written as like this, because nitrogen is sharing three electrons with two nitrogens, and this nitrogen is sharing two electrons with oxygen. So calculate the formal charge of each atom present in the nitrogen molecule and write the structure of N2O. This is the structure of N2O is already given. So first let us see uh, formal charge of this nitrogen, second nitrogen, and first nitrogen. So we can I hope I'll just make it clear. So how to calculate formal charge of first nitrogen? Let us see. This is for your this thing. So it has how many valence electrons? 6 total. This nitrogen is having total 5 electrons. So first let us see this nitrogen. This nitrogen formal charge is equal to first nitrogen I'll show, second nitrogen you can do it. So only nitrogen only we have to show. Formal charge on each atom of present in the molecule. So oxygen also we can calculate. First let us see nitrogen. So nitrogen here, number of valence electrons is 5. So number of valence electrons is 5 minus 1 by 2 into number of shared electrons. How many electrons it shares? Total 3 electrons it shares. So 3 plus 3 total it is 6 minus number of unpaired electrons, that is unshared electrons, that is 2. So minus 2. So it is 2. So 5 minus 3 minus 2. So formal charge of first nitrogen is 0 because 5 minus 2 ones are 3, 2 threes are. So it is getting 5 minus 3 minus 2. So minus 3 minus 2 becomes minus 5 minus 5 minus 5 gets cancelled 0. So first nitrogen formal charge is 0. Second nitrogen, let us see now. Second nitrogen here, it has how many total valence electrons is 5. For second nitrogen I'm writing here. Second nitrogen 5 valence electron does not change, and number of electrons shared. Number of electrons shared is minus 1 by 2 into. For this the sharing is more because this side it is having how many it is shared 6 and this side is shared 4. So it is shared 1, I think. Yeah, one electron for this nitrogen, for one electron on this side. So total it is 6 plus 2 8. So minus 1 by 2 into 8 minus number of unpaired electrons 0. So for this nitrogen, formal charge becomes 1. I hope it is clear. Now let us take consideration of formal charge of oxygen. Oxygen, total how many electrons it is having. Formal charge of oxygen I'm writing here. Oxygen formal charge is equal to, for oxygen, formal charge number of electrons in the valence shell is equal to 6 because oxygen has 6 valence electrons minus 1 by 2 into number of shared electrons. It has only 1 electron shared, so 1 plus 1, 2 minus 1 by 2 into 2 minus. And how many unpaired electrons? 1, 2, 3, 4, 5, 6. 6 electrons in the unpaired. So 6 electrons. So actually it is 5 electrons actually. So we can take 6 minus 1 minus 1, 5. It is total, it is equal to 0. So the formal charge of nitrogen is, first nitrogen is 0, second nitrogen is plus 1, third oxygen is 0. So I hope it is clear. In this way we will calculate formal charge. The formula is simple. What is the formula of formal charge? Number of uh, that is number of valence electrons of central atom, that is the main atom, minus 1 by 2 into number of shared electrons minus unshared electrons. I hope it is clear. So 0, 1, and here it is also 0. So 0, 1, 0 is the answer. So we can do formula just like this. I hope it is clear. So next question. Next question. Again, it comes around apply Vesper theory to predict the shapes of SF4, ICL3, PbCl, and H4 plus. This Vesper, after finishing valence shell electron pair theory, we'll discuss these shapes. So meanwhile, we'll not discuss these shapes now because suddenly this question has come here. So I hope it is clear. Now I'm ending this session. I hope you understood clearly. So lecture 2 is completed in chemical bonding. In this lecture 2, we have done completely about covalent bonding, and also very important concept in this topic is formal charge, and also Lewis dot structures. It's clear. So whatever I explained here, clearly you mention that and do it clearly. Make a classwork. First maintain a classwork notes. Whenever you get a slide on the screen, first you write the slide, then listen carefully with your earphones and apply the concept. Easily you can understand all the concept like physical class. I hope you try to understand better and better, so it will be easy for us. Thank you all.